that is because this is very sensitive to noise. If V1 gets a slightly bigger than V2 or a slightly smaller than V2, VO jumps between VCC plus and VCC minus. Using a Schmidt trigger, you can have a threshold. So basically you can just like adjust like how much changes is acceptable before you change the voltage, right? But anyways, I just wanted to tell you that we have concept of comparator that we can use, and this comparator like have like two output voltages and it switches between these two. That's exactly what we want. We want to create a a square wave signal, right, that jumps between two voltages, and we want to apply that to our gate, right? So like let's say we want to have apply this to gate 1, right? It turns on or off, on, off, and so on. So this is what we want to do. So what PWM is basically generating these signals, pulse width modulation, and modulating the width of the pulse. So modulating the width of the pulse. Okay. So if we have what we just saw before, something like this. This is just like one pulse. And we saw that this has a lot of harmonics, right? This doesn't look sinusoidal. If you calculate, if you take a Fourier transform of this and calculate the THD, you will see that it has a lot of harmonics, and we saw that the current also doesn't look sinusoidal, so that the current didn't look sinusoidal. And why is harmonics bad? I wrote many disadvantages of, or like many problems with having harmonics. So first of all, if you supply this voltage to a load, which is like, let's say, a motor. If you supply this voltage to a motor, you're basically, your motor is gonna have torque pulses, or you're gonna have like a pulsating torques. Like basically your motor is not going to be running smoothly with just like jumps and jumps and jumps. So that's not ideal, right? And that would basically make all the windings loose and eventually reduces the life of your motor. And of course, like let's say like you want to use this motor in the elevator, like it's not going to be ideal. It's going to have like jumps all the time. Or if you want to use it like in let's say in a mine industry or like textile industry, it's not going to be ideal, right? Like it's basically it's not acceptable at all. The other problem with the harmonic is, so like the first problem was like having pulsating torque, and we would also have like insulator damage, because let's say we did the insulator coordination for a certain voltage. Now we're gonna have a lot of harmonics, so it basically increases the voltage, and you might have, let's say, like 200 volt 60 hertz, but you have additional 120 hertz, 180 hertz, and so on, like first, second order, third order, and like many like higher order harmonics, and it would damage the insulation. It would like cause overheating, and of course losses and poor power quality. Excuse me. So if you want to supply this to the grid, let's say BC Hydro wouldn't buy this from you, because this is not acceptable. It has a lot of harmonic. If they inject this voltage to the grid, it would cause us a lot of problems. So this is not acceptable. So the solution for that is to basically to reduce the harmonics, is, instead of having a single pulse, is having a train of pulses. How is this done? How is this done? It's using the same concept that we saw. Let's say here, like, we have 0 volt, and here we have like whatever voltage that is needed for our switches to turn on. So here what we do, we use a comparator to generate a PWM signal. And the type of PWM that I'm discussing in this course, it's sinusoidal PWM. Okay, so what does that mean? It means that one of the inputs that goes to the comparator, it's a sine wave. And the other one, should have done it better. The other one is a sawtooth waveform, or a triangular waveform. They shouldn't have the same frequency. This one has like higher frequency. So something like this. Okay, so this is basically how we generate the gating pulses for our switches, right? We have to turn switches on or off, right? So we have to control the gating signal for those switches. How those gating signals are created is using sinusoidal PWM, or like there are other PWM methods, but this is one way of generating PWM. So for example, if we have something like this for our sawtooth waveform, and we have, let's say, didn't do a good job, but like, let's say, like, if this is what we have for sine, which is our VP, and this is for our VN, right? Then our output, it's gonna be a square wave signal, right? So whenever VP is bigger than VN, output, it's gonna be on, or like we basically switch the MOSFET on, or like the IGBT on. Whenever it's the other way, it's gonna be off. Okay, so like this is basically, let me just like do this and then draw this for you. Maybe I'll just do it for one period. So this is, so here, if